Hi everyone, and welcome to today's session. Today we'll be talking about a very exciting new model by OpenAI. It's called O3. Essentially, it is a similar method to O1, where they train the model on better and better quality data that is generated by its own outputs. So it's trained to output reasoning tokens. And then if you fine-tune on these reasoning tokens, provided the reasoning is correct, you should get better and better performance for certain tasks. So this actually, in the last video I did about O1, I was thinking, why can't you just do this reasoning reflection via an agentic system? And I realized that, by doing this training of tokens that you generate from the model to do better reasoning and you fine tune on it, you actually improve the base model. And so this base model improvement is hard to replicate with an agentic structure. But of course, you can use the agentic structure over this O3. So what's the main thing that I've taken away from the performance? And if you are aware of the benchmarks, they actually scored about 85% for the ARC-AGI benchmark, which was quite significant to me because I spent a lot of time doing that benchmark and I could hardly get above 40% for the test set, for the training set. So this is quite significant for me. And I think this shows that there's something right about the way that they are training the model. And I think that something right, if done properly, it could be used for self-improvement. So let's take a look at how this is done and what I think can be further done to improve the performance. So first, let's just do some primers because, O3 is not an open model. They didn't give any architecture or anything. Let's try to analyze from first principles how possibly such a model could be trained. So first, let's take a look at traditional deep learning. So as you know, deep learning is data-driven. So it needs a lot of good data to do well. So back then in the days of 2014, ImageNet and so on, people use supervised learning where basically you have an expert label. So like, for example, you have a text and then maybe you give the sentiment, or you have an image and then you give the caption or something like that. So you have an expert label that you want to get the model to learn. And this basically is supervised learning. Eventually, we move to the era of self-supervised learning, or some call it unsupervised learning. And this basically is given a set of tokens, like the cat is on then you predict the next one, which is math. Okay, so this kind of learning is much scalable because you don't have to have any human labeling your data. You can just use those data that you find online and simply mask out certain sections of your data and predict those. So back then we had BERT where you just mask out 10 to 15% of your tokens randomly. And then you have GPT, which masks out the next token. Yeah. So in the end, it turns out GPT scales better. That's why OpenAI is doing so well now. And this also kind of hints about how perhaps the brain might learn. It's been said that the brain is a prediction machine. We try to predict our next state and so on. So by simply just predicting what will happen next, that can actually get your system to learn a lot about the world structure. It will learn a lot about how causal relationships are formed. And I think this is quite cool because you can just take the web data, you mask out the next token, and you can just train on the entire corpus on the web. So we have been doing this for, I think, the last 2 to 3 years. I think even more than that. So people have taken lots of data from online. There's also a lot of corpuses that have been created, a lot of data sets that have been created based on web data. And then people just fit inside this transformer. So I mean, the most notable ones are like the PAL, there's version 1, version 2, and so on. So this kind of data is used to train the transformer. So they tokenize, scrape the web data, or take those kind of public data sets, tokenize the text, or you have image encoders, you can tokenize your image also, tokenize audio, but mainly text, especially on what we're talking today, we focus on text. So we predict the next token like this, the cat is on, then you predict the, and the cat is on the, you predict mat. And all these things, by predicting the next token here, you sort of learn how you do all your attention weights over here and how you learn the kind of structure between your tokens, how your token embedding should be. All this can be learned just by simply predicting the next token. Of course, for those who are familiar, you would know that GPT doesn't have the encoder branch of the transformer. They just use decoder only, while BERT uses both. Yeah, so this transformer architecture itself, in my opinion, the exact architecture is not as important as the ability to do attention plus learn next token. So I wouldn't be surprised if like there will be a different architecture that will take over next time. But the attention part, as well as the kind of token prediction for the next token, I think will likely still remain. The intermediate steps might differ. So yeah, that's how people have been training large language models. Like a lot of companies, Google, Anthropic, Meta, they all use some form of web data, train the transformer. They scale up the transformer parameters, 7 billion, 13 billion, 405 billion, and basically hope that the model kind of consolidates what's online, and maybe you fine tune a bit on the data sets that you like. So they call this step supervised fine tuning. And then after that, you might even do some preference alignment, and they call it RLHF, reinforcement learning from human feedback, or direct preference optimization. Okay, so this kind of things is like how we have been training so far. Okay, if you know me, I don't really like this kind of steps like RLHF because I think it biases too much to human preference. You might end up getting hallucinations and so on. Yeah, but the whole idea of fine-tuning on the web data has been ongoing for a while, and it has been quite successful. It has reached high benchmark scores. If you look at the GPT-4 papers and so on, it's not bad, but there's a slight problem here. And anyone can tell me what's the problem with just training web data? Any guesses?
I think I have the immediate answer. The web data is going to vary too much in quality. It's too randomized almost. There's no guarantee for high quality data.
Yes, that's one reason for that. And the other reason is web data is only so much. After you have trained with all the web data, you want to further improve in your tasks, like your target tasks. Like let's say, for example, you're doing finance, and or maybe you're doing a language that is not represented very well in the web data, maybe African languages and so on. You find that you can't really get the kind of data you need from those kind of, like, from just pure online sources. So what do people do? So as what Derek said, web quality of data online is very important. So people have tried to improve the models by curating the data more. So like if you look at the Llama 3 paper compared to Llama 2, Llama 2 they say they took in all the data from online without curation. And Llama 3, they said they filtered quite a lot to make sure the quality is good first before you use it for training. And it turns out the quality is very important, because if you give it garbage, it will learn the, the relations there and you will get garbage output. So it's like garbage in, garbage out. So if you could have a way to have better data, it would be much better in terms of your model output. And another thing that a lot of people are doing right now is to use expert data. So domain-specific data sets that are proprietary. And I mean, OpenAI is doing this quite blatantly. They have partnered with a lot of benchmarks makers, like for example, ARC-AGI. I think they're also partnering with Frontier Branch to make the benchmark, to co-create the benchmark, so they can use the proprietary benchmark for themselves. Yeah, so expert data is quite important because that kind of data would help to provide the kind of output quality that a higher level analyst would need. So this expert data can be generated from humans, like maybe PhD students. You ask them to write some rationale for solving math questions, Olympiad questions, and so on. It could be data collected over time, like news corpuses and so on. So this kind of expert data are great. It helps to improve the model output quite significantly. I don't have the numbers because I don't work in big companies, but I'm very sure that this is what differentiates a lot of transformer models. Okay. So the problem with kind of this data is that you will still run out of such data. So we have reached a point whereby you want to train on more data, but you realize that you are lacking those data. I mean, of course, there's other data that you can have. You can have usage data, like for example, people using ChatGPT, Gemini, and so on. You can if you own those services, you can use those data and train over it. Okay, but there's a limit to what you can do with all this. So we kind of need to think about a new paradigm, whereby instead of just providing all the data like this slide, can we use the model to generate the data? And I mean, one of the papers that did it pretty well is that they use like teacher model, like for example, GPT 3.5 or GPT-4, that's got tiny stories. You use it to generate like short text of stories and manage to train like GPT-2 to reach quite a similar level of performance compared to the GPT 3.5 models. So something like this, if you could just prompt the model somehow to generate the data, like maybe you can say like, generate me data of this format. And this data could be very, very similar to the kind of expert data you find online. So if we can somehow get this, we might have an infinite loop of data that you can use. Okay, but of course, this comes with its own problems. So the question is, can we generate our own data like that improves upon the original data and just keeps using it to self-improve the model? And there's some caveat here. The answer is actually potentially yes, you can use this to self-improve, but you can only improve it to the kind of distribution that you generate here. So one example for this in real life is I took part in a hackathon last year. It's called the LMs for Bio hackathon. And in there, my team did like description of a protein and then map it to an amino acid sequence. So I went to train GPT-2 on this kind of things. And I realized after that, when I asked the the GPT simple questions like, what is the capital of Paris? And guess what it gave me? It gave me the amino acid sequence, blah, blah, blah. It gave me this amino acid sequence, which kind of shows that because of my fine-tuned data here, it kind of gave me something that matches the data that I fine-tune it with, but it lost the ability of the original model to tell me, hey, this is actually, oh, sorry, what's the capital of France? Say wrongly, yeah. France is Paris. So it lost the ability to do general questions like this because of this data that I generate, and I use this to fine-tune. And if you look at the technical reports of Meta and so on, you realize that the data that you want to be most targeted with, you fine tune at the end. So they fine tune more for like math, coding, and so on towards the end in the supervised fine tuning phase to better target those benchmarks. I'm actually very sure that most major LM companies do that. They fine tune the benchmarks that matter at the end of their training. Okay, because there's such thing called catastrophic forgetting. Like if you train stuff towards the end, the earlier stuff might be forgotten in the LM weights. Okay, so there's some problem with this, but it will do quite well for the data you are targeting at. So if you generate expert data in that particular domain you are interested in, and you fine tune it, the transformer, you might get better and better kind of data. Okay, but this of course comes at the cost of losing the generalizability. Just a quick question to all of you all here. Anyone here has fine-tuned LM models before and realized that you get a similar kind of like finding from me to me? Anyone? Anyone fine-tune models before? Okay, no worries.
Yeah, but,
Yeah.
but I didn't purposely try after fine tuning. I didn't purposely try all of distribution. Like the prompt there all is all of distribution of your fine tuning data. So yeah.
All the I was gonna say all the fine tuning I've done hasn't been like the large language models. It's been much smaller models. It's been like with LoRa adapters, but yeah, I think you've heard my thoughts before. Like anytime you fine tune something, it feels like almost like lobotomizing. Like you're really brute forcing the layers and bending them to do something, but you're also kind of breaking it, right? Because now it doesn't have that nuanced generalizability from before. You're kind of forcing it to conform to a certain way. So now it's good at something, but it's very brittle, very focused on one task that is fine-tuned for exactly.
Correct. So this is the problem with generating data and using it for training. One is that it might overfit a lot to that kind of data. And actually the second problem is that, this data may not be correct because, if you generate data, you have no guarantees about the reliability of the data unless you have some ground truth. And that's a good segue into our next slide.
Sorry, can
How
I
yeah,
check in
yeah.
here for 2 related points?
Okay, yes, sorry.
First is on the topic of fine-tuning with LoRa, right? I would guess, I would imagine that if you fine-tune with LoRa, then you should have less of a catastrophic forgetting problem because you are not changing the parameters of the base model by that much, right?
Yes,
So
if you fine-tune with LoRa, you may not get significant performance gains, but you also will retain the original model weights.
that's one thing. Another thing is, uh, I feel like this problem, the category forgetting problem, is more severe for smaller model like GPT-2. And if you have caught up recently, Anthropic shared like one of the finding is the larger model. I think they did experiment on Opus. They find that the model is actually reluctant to your fine tuning or alignment to the point where it actually fake the alignment. So on the surface, it seems like it already changed its output distribution, but then actually underlying weights are still not changed that much. Yeah. So my current gut feeling is, yeah, as you scale up the model size, this problem of fine-tuning actually will not change the distribution as much because you simply have too many parameters. Yeah.
I mean, that's an interesting point to note whether we can minimize catastrophic forgetting with larger and larger models. Then in that case, you can train with more and more data and it won't affect the original data. That's the ideal. So maybe we'll reach that point, or we have already reached that point. I'm not too sure. So if that's the case, then then this procedure will work quite well. Like you can just keep fine-tuning with data. As long as this data is correct, what you will get is you'll get a better model performance without sacrificing the earlier bits of it. So the next question we need to ask ourselves is, how do we get this expert data? So how do we get the data ourselves? One way is to, prompt it. If you look at a tiny stories paper, they just prompt it to generate stories with this vocabulary and so on. So, if your model is general enough, you should be able to get the data. Right? I use this quite often also, like I want to generate some kind of ideas. I just prompt it. And that kind of data that you generate, you can perhaps use it for tuning your model for that use case that you are interested in as well. So, I mean, if you take a look at the probability distribution, like let's say initially the model is outputting like this, model is outputting like the cat is on the mat, and then you keep fine tuning it to the cat is on the floor. I mean, soon you will adjust the token probabilities to your fine-tuned data. So it's very likely that, if you want you want to target certain kind of distribution, you keep asking the model to generate that kind of distribution. Like maybe you can prompt it. So the prompt for this kind of thing would be like, you prompt generate locations on the floor or something like that, or the sentences. Change locations to be. Yeah, so you can do some prompt like this, and then you can change like the cats on the mat to the cats on the floor. They keep training the cats on the floor into your into your model. You will be able to kind of shift the token generation probabilities to make it more and more towards like floor. Okay, but you must be very wary about something. When you fine tune data, okay, if data is too out of distribution from original pre-training data. So pre-training data is the data on the left just now for that slide, the web data and so on. If your data is too out of distribution, okay, what will happen is you will hallucinate more. So there's a paper that talks about this. Can't remember the title. Probably link the title later on the video once I remember it. So the thing is, you can get this expert data, you can fine tune it, but you must make sure that this data is similar distribution to your original pre-training data. So there's also another paper that talks about like how much can you do scaling the test time compute, and they realize that if your test time is like much more than the pre-training, you won't do that well. So your pre-training data is still very important. So this expert data you generate should be quite similar to what you have in your pre-training data, right? But you can generate more synthetic data by just prompting the model and so on. And the thing is, there's some techniques that you can use to ensure that this data is pretty reliable. So one way to do it is, instead of just generating more data, you could generate Like for example, problems that require some form of chain of thought, you could generate the reasoning and put the reasoning together with the data set. So later there's a slide on the star model. So I'll talk more about the reasoning part here. You can also get better quality by sampling the model more and filtering with the ground truth so that your kind of data that you get is very, very close to an expert data because I mean, you may not be able to verify the procedures, the steps, but at least you can verify the output is correct. All right. So what if there's no ground truth to verify? Then there's a slight problem here because you may be generating expert data that is wrong. And if you fine tune on the wrong data, your model actually can be worse. So how do we do this? This we'll leave it for discussion later.
Hi, can I ask a question here?
Yes.
So you mentioned the point that your fine-tuning data cannot be too out of distribution of compared to your pre-trained data, right?
Yes.
But I find it's hard to define out of distribution here because no matter how you filter your pre-trained data, it's still for all intents and purposes almost the whole internet, right? That means it already cover all sort of distribution. So as long as it's something that's syntactically correct, I believe you can find it somewhere in your pre-trained data. In this case, like I find it hard to see what kind of fine-tuning data is out of distribution. You get what I mean?
Yeah, I mean the kind of things that I think the paper did is like incorrect data. So it's like data that directly, goes against what your pre-trained data is. Like for example, your pre-trained data can say the house is blue, and then your fine-tuned data, the house is red. Then
Yeah, but the thing is, I believe maybe the experiment conduct on very
small
for
data,
example, so
small
they
models, right?
pre-train on very limited, but for practical purposes, the frontier model are pre-trained on, almost the entire internet. So for the house is blue, I think you always can find the house is red also in the pre-trained data. You get me?
Yeah.
It's so complex. I mean, the distribution of pre-trained data should be very, very complex that it almost cover all the syntactically correct case of whatever you can think of. That's my intuition of It's just so intractable. So I don't know how do you define it for a practical model. What's all of distribution? Yeah.
Yeah, I guess it's like, the amino acid sequence that I showed you that I talked about earlier. Like if it's something that is not very common in the pre-training data set, you might
Okay, that one I agree because if that one you can create a random string that's not found anywhere, then that's all of distribution, I guess. Yeah.
Yeah. So anyway, that paper is talking about some of the pitfalls of fine-tuning. So I just highlighted it here because if we are going to do this self-refinement loop and self-training loop, we kind of want to make sure that your model doesn't go haywire with the other stuff as well. You want to preserve the sanity of your model. So I think what you will likely do is you'll put that data set that you want to fine-tune. You'll put some version of it in your pre-training as well. Yeah.
Yeah. I think I saw somewhere some technique involves you already put fine-tune part of the fine-tuning data as used in your pre-train phase. I think it helps somehow. I don't know, but I
Yeah.
saw such technique being adopted. Yes.
So I'm not an expert with fine-tuning very large models because I'm not from OpenAI. So if one day, I can find someone who's able to share some stuff, I'll invite that person to share here. Yeah, I think it's quite interesting to see, how things can change based on where you put the training, like pre-training or fine-tuning. But here today, we are focusing more on the fine-tuning part because that is what the O1, O3 models do. They actually train on data that is generated by themselves. Okay, so let's see how we can do this. So again, we don't really have the details because OpenAI is quite secretive, but we have some open source papers that talk about how this might be possible. So this is the self-taught reasoner paper called STAR. And I think this paper was very interesting to me because what this paper does is that, when you do chain of thought, like for example, you want to solve a math problem or solve a certain problem, you have a question here. And then if let's say you have a thoughts here, you can put your thoughts and then your answer. So by doing this method of getting some thoughts out, and best if it's a structured thoughts, like first you do this in this aspect, they think in this other aspect, and so on. So if you can have some structured thoughts and you use those thoughts to condition your generation, because LLMs generate token by token. So if you have these thoughts or your context up here, you generally will get better answers, like especially for kind of questions that need a bit more thinking. Yeah, it's best not to do something like, so stuff like question to answer directly, question, then the answer. This one doesn't do that well as compared to chain of thought. So the thing is, this paper is thinking that, if chain of thought does so well, can we fine tune the model with the chain of thought, with that rationale? So take a look at this example over here. And this example here talks about like what can be used to carry a small dog. And this is the rationale, right? And then answer is B. So the thing is, when given the question, okay, and if let's say the answer is correct, okay, we ask the model to output the rationale and the answer. And if the answer is correct, in the fine-tuning data set, we can add back this rationale here so that, when the model generates things, it knows what is the correct rationale, because, it's somewhat like validated by experience. You already know that this rationale should be correct because you got the right answer based on the ground truth. Take note that you have the ground truth answer so that you know whether your answer is correct or not. So if the answer is correct, we kind of assume that the rationale is correct. Okay, so this is an invalid assumption, okay, because your rationale can be wrong. You can actually reason wrongly and get the right answer also. So, but you hope that in the long run, the rationale is correct when your answer is correct. So you fine tune on the rationale in the next cycle. Okay, what if the answer is wrong? Okay, then obviously your rationale here is likely going to be wrong. So what they do is quite interesting. They just basically ask the model to generate the answer by just giving it, like, for example, if basket B is correct, they will just give a hint here to the basket. They'll say this is correct in the question, and then they'll ask the model to generate the rationale and the answer. So they already gave the correct answer in the question, and through that, we again assume that this rationale is going to be somewhat correct because the model will just rationalize to get this answer. All right, and if your model knows some other context, so on from its previous training set, it might be able to give the right rationale. So I mean, an analogy is like this. Suppose I give you a math question, like for example, I give you a question like, what is 5 plus 5? Okay, maybe you don't know the answer, but if let's say I say the answer is 10, then it's like, oh yeah, 5 plus 5, 5 hands plus 5 fingers plus 5 fingers is 10, something like that. You might be able to get the answer by just thinking from the answer and trying to, backtrack and give some reason for it. So this, I think, has some use. Okay, but again, I would like to highlight something. All the rationales that are generated has no guarantee that it's correct. Okay, it has no guarantee. You know why? Because it's still generated by the model. So this is a very nice way to imbue some form of chain of thought into the data set. And then by fine-tuning on the rationale or the chain of thought, you might get stronger answers because you already know like this set of, I would say this is the bootstrap rationale, bootstrap chain of thought. Basically, you try to get like a certain way of doing reasoning from your original data set. You try to get that from your original model, the rationale, and then you try to fine tune on it. So it's something like knowledge distillation from yourself. Like, so for example, if you have let's say you have maybe you already know how to do the reasoning beforehand, but once you make it explicit, if you make the reasoning explicit, you can prompt less. Yeah, so because by training on the rationale, you are able to get the model to, by default, output those rationale as well. And in this case, it matches the training distribution or the output distribution that we want it to do. And then, it's a self-reinforcing loop. Like you are making the fine-tuned data more and more similar to the target distribution. So if this is done well, yeah, I mean, you could potentially keep improving until your model gets the wrong rationale and it doesn't work anymore. So they got like 5 percentage points on the GSM 8K data set by doing this method. I think it's 5%, like improvement. or 40% improvement. I can't remember. It's a significant improvement, and it shows that, you know, some simple things like this that, you know, you could ask the model to do like chain of thought directly, but it's not as good as if you were to give whatever it has output before and you fine tune it, then you ask it to do chain of thought again. By fine tuning it and asking it to do chain of thought, it gets much better performance than just asking it to do chain of thought without the fine tuning. So there's some merit to this idea. And I think this is one of the basis for O1, O3 models, that they use some form of bootstrap learning from the model's original output. So we look back to the diagram here. The expert data here that is generated, that may or may not be correct, but you have a way to robustly, you know, identify the correct ones through maybe filtering by ground truth and so on. It might be very useful to train the transformer model on it so that your target distribution is better and better catered to. So then lies also a little bit of problem with O1, O3 is that if you ask it to do very simple things, it might overthink. Okay, but recently I've been playing with the O1 model on OpenAI, and I realized that I asked it to do simple things, it didn't do any reasoning step at all. So maybe they have a filter to, you know, use for O when it's a simple question. So this is my suspicion. But yeah, if you were to use a train process like this, you think about it, if I keep telling you that everything is complex, everything is like there's some nuance in the words, you might overthink even a simple sentence. Okay, so this is the effect of fine-tuning. Like you will get closer and closer to that target distribution that you fine-tune. So you need to be very sure before you do this process that this is what you want from your model.
But I feel like it depends on to some extent on the diversity of your fine-tuning data, right? For example, if in your fine-tuning data, you also add in the very simple type of question with very short reasoning steps, then the model might also learn for simple question. It does not need so many reasoning steps.
Interesting. Yes. So in the fine-tuned data, put in more distribution of data, like simple to difficult problems, right? And then you can get the whole range of responses that are needed. And actually, that's a great point. So it is very likely that you can do some form of engineering of your fine-tuning data set that uses this self-refinement approach that can do both complex and simple tasks. Because if your simple task is in your distribution, you will learn the simple task as well.
But I think this approach also has its own limitation. Otherwise, O1 won't give you a parameter to control the reasoning effort. It can be fully automatic. But so I guess there's some like there's a limit you can achieve with this kind of approach. Yeah.
Correct. But that's why you see when OpenAI advertised O1 or O3, they didn't say it's GPT-5, you see? They say it's better for reasoning tasks. And this is because when you fine-tune reasoning into the model, you know, it will be better at the reasoning task, but it may not be better at the rest. Yeah. So I think in general, it is great to have for such domains because, you know, you can make the base model better for such things. Because, you know, online, when you get online data, it's very rarely you will have rationale for everything. It's very rare. But by digesting online data and asking to get the rationale and have some form of filtering to the ground truth approach to augment the data set again with the rationale, this will actually increase the model's base performance if this rationale is correct. So actually the question I have to ask, like this is a question that I have no answer to. Is it possible to get the generated expert data and use it as pre-training to another model? So we don't even do this fine-tuning step. We just augment the web data with this model distilled data. And can you do this? And I've been reading a paper called The Journey or something like that. So basically they try to do some O1 open source thing, and they've realized that by fine-tuning or by using O1 responses to train like an LM, they get better performance than O1 itself for the math questions. So I think this opens a lot of paradigm because like now, since we can use the LM or the transformer to generate more data, can we just use it directly at the pre-training step? Okay, this is an idea that we won't be discussing too much today, but this is just food for thought.
Wait,
Yeah, please go ahead. Sorry.
I thought this is exactly how they made O1 mini.
I realized now even GPT-4o can solve like strawberry questions. And I suspect that, if you use the O1 logic and train on the 4o, your 4o might be better performance at that kind of distribution as well, even without explicitly asking for chain of thought at test time.
Yeah, I do see such speculation somewhere as well.
Yeah. So the idea of the mechanics, exact details of the mechanics, I don't really care too much. But the idea is that you can get more data from the model itself. And that's interesting because what kind of data can you get and whether this data can be used to improve the base model. And that self-improvement part, very, very interesting to me. Yeah. Any other questions before I move on? Okay. Can anything just let me know if you want to talk about stuff?
Sorry, just a very short clarification. Here in this paper, by fine-tuning, you mean they mean SFT, right?
I believe so, yes, SFT. So it's not a direct fine-tuning of a base model from scratch. You fine-tune the model that you use to generate this. Yeah, so
Okay.
you can treat it as SFT. Okay, so the next thing is something that I'm very interested in because it's very related to the brain. So this is about mini columns and sampling. So if you know my previous kind of sessions, I've been very fascinated by psychology, neuroscience, and so on. And there's this thing called the neocortex in the brain with the cortical sheath that have this thing called the mini columns. And these mini columns, we have the most out of any species on the world. So if you look at the chart next, with the overall brain volume, which also like corresponds to the mini column volume, like you can see that as it increases, the neocortex volume increase. All right, your brain volume. Okay, so actually this graph is not about intelligence, but if you look at this graph here, you realize that by any measure of like intelligence, the human brain, by having like more neocortex, we can actually do a lot more tasks than maybe the chimpanzee and the rest of the things that you see here, the mouse also. Yeah, so perhaps there's something to do with, the more of these columns, the greater the intelligence. And why. And my rationale or my hypothesis is that it enables you to do sampling. Okay, because like maybe one mini column can process one thing. You have a million of them, you can process a million things in parallel. And maybe processing this in parallel and then combining them afterwards might be able to get some improvement. And okay, this is the next slide about multiple sampling. Anyone has heard of Ryan Greenblatt? Anyone? Just raise your hand or let me know. Who has heard of him? Okay, Derek. Okay, so this made news quite recently because he got like 72% on his eval, but after testing is about 50%, I think, for the test set. But this is an impressive thing because what he did was basically he just asked the LM. I mean, there's a lot more details, but the crux of it, he asked the LM, given the prompt, generate more answers. So you can see over here, this K is the number of answers that are generated. So the more answers that are generated, and then you just filter by seeing whether your training set for ARC, meets the requirements. So mass sampling and filtering. The more you sample, the higher your accuracy. Can you see that? Yeah, so it means that if we are able to scale up the number of samples we get, you could perhaps increase the performance on all the benchmarks available out there right now for LLMs. Yeah, that's because one path of the LLM sampling might hit the right answer. So this is very, very simple idea of getting more samples and perhaps filtering them with some ground truth because you want to make sure that the sample you take is something that is useful, not just a random sample. So you can take more samples, filter with a ground truth, you can get better accuracy. So I want to answer the question of what if there is no ground truth? Like you ask O1 to do a question, but there's no ground truth for your question because it's yours, it's a new one. It turns out that I think I have this in the later slide. It turns out that you could just do majority voting or majority consensus, and it works quite well. So majority consensus can get you an answer. Basically, what this means is that I ask maybe the model to sample 10 different times, 10 different trajectories to get your answer. I see the answer and I just see like, okay, maybe answer A appears 5 times is the most common. Then I answer back to you is answer A. So it may be that, as long as there's a majority consensus, there you go. that's your answer already. So this multiple sampling and voting is also used in other stuff like random forests, where you sample multiple kind of similar models that you maybe omit some of the original data for each of them, for each of the decision trees, and then you do some majority voting. Works very well. In fact, one of the best performing algorithms for Kaggle competition still remains random forests, or I mean, it's now called a XGBoost, but I mean similar idea. So this idea of sampling voting has been around for 20 over years. Can't remember how long, but it's still good. So can we do such multiple sampling and filtering or majority voting for LLMs? And the answer is yes. So very simple idea.
Oh, sorry,
Yes.
one question and one comment. So the question is, can you go back to the previous slide? So the y-axis, is it the average accuracy of the top three, or is
Okay.
the best of the top? Oh, yeah.
Yeah. So in ARC, maybe I go to the ARC now. Like in ARC, when you get like this the input and this the output, you want to get from the input grid to the output grid, you have some training examples that are given to the model, and you have the test example. So in this case, the answer is to fill up the enclosed squares, right, for this grid. So when you actually submit to ARC test set, you can submit up to 3 guesses. So when they say top 3 accuracy, it means that if any of the 3 guesses are correct, then we count it as correct.
Oh,
Yes.
got it.
Okay. So that's
Also, one comment is regarding the majority voting, right? I saw from one YouTube channel which is quite good. They
which
this
version?
this this person came up with his own benchmark called small bench. It's testing some mode in which most the element always feel very badly. And in that case, he tested O1 Pro, which presumably just increase the sampling steps compared to O1, and it get worse on his own benchmark. So I guess that might suggest this method doesn't work for all domains. Maybe for most of domain, but there are domains naively just increase the sample size may not scale as well.
Correct. Like for example, math proofs and so on. Like if your model just cannot solve it, even if you sample many times, you also may not get an answer. Yeah.
Yeah, but I think that bench is like more spatial reasoning. Yeah, like it's for human, it's very common sense. Like, so for human, it's like ARC. It's for human, it's easy to get high marks, but for LLM, it's hard, that kind. And it doesn't simply just scaling doesn't work there. So I think it's like a caveat, because I guess for most of cases, scaling up the sample size still works. But I just want to caution that maybe it's not for all domain. It doesn't work. Yeah, it doesn't always work.
Yes. Yeah. So actually, I do agree with that, and that's why I say that this method has some limitations. But let's suppose you want to use this method, and I think the multiple sampling method works very well, because if you can use a model and you combine it with instructions. So I realized that for like large language model, your in context prompt can change the model output significantly. So what do I mean by this? It's like, for example, if I ask you to output in Shakespeare or output in pirate language, you know, um, it will give you very, very drastic and different outputs, like for example, an essay and so on in this with just this prompt alone. So this is called like a mutation prompt or context prompt. And this enables the model to get different kinds of responses. And imagine if your prompt is something like, think step by step, or the prompt is something like, um, question all assumptions. So I think there's a paper by DeepMind. It's called Prompt Breeder. They try to get the best prompt to, solve math questions, and they turn out that the best prompt is take a deep breath and think step by step or something like that. Yeah. So if you can condition your model with a certain kind of prompt like this and ask it to generate stuff, and you can sample many, many times for each instruction, it's something like, okay, if you have a search space here, I just draw a triangle here, the search space. Each instruction is like covering a certain part of the search space, like here. And this search space 1, this search space 2. You are trying to try your luck to see whether you can get an output that will match the ground truth, or to match the answer that you need. Yeah, and this is just for one agent, by the way. This is just for one agent. If you can have a multi-agent system, each agent has different personality, has different data for grounding. You might be able to get different kinds of diversity. And so, this generates samples, but by asking it to do different conditions, you are like mimicking different kind of personalities and so on. The next step will be like different kind of pre-training data. You can get different kind of output also. So, OpenAI has a lot of models, so they might be already doing this multi-agent generation. So, I mean, in my framework for Agent Joe framework, I also intend to scale up to multi-agent with multi-agent diverse generation, and then all of them can consolidate and learn from one another. Although not all of them will learn, because you still want to preserve some of the earlier versions, just in case you fine-tune too much to the wrong distribution. At least your earlier version can still work if the environment changes. So this diverse sampling is very important. How to diversely sample is a study of research for very, 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 very long time, right? And I think there's many ways to do it. Yeah. So one way is just to do what I'm saying here. Just use the LM and just generate. Okay. There are other ways. Like for example, you can change certain parts of your data and then you ask it to sample again. Yeah, I'm not going to go through all the ways because there's just too much. The main thing is generate diverse samples. Use whatever means you have at your disposal, generate them. Another way to get better results for diversity is to just have more ground truth data. And this is very pertinent in the ARC challenge. So I have a friend, uh, basically Michael Hodel, he basically generated synthetic data for the ARC challenge for all of the training set data by hard coding some parameters. And then if you tweak the parameters, you can get different generations for each of the problem. And this helped his team like get one of the top performance for at least for the benchmark before this OpenAI results release. So synthetic data actually can help you to get diverse samples, and especially if you could showcase the different ways to solve a problem for just one problem, you might be able to make the model think in different ways without being stuck in one direction. So this is again a slide that requires further research, but generating diverse samples is very, very important. Okay, so this is important because now we have an infinite possibility. We have infinite possibilities for the data. I mean, back then when you talk about, chess or Go, your move is kind of fixed out of a certain fixed move. But if you talk about a stream of tokens, there's infinite possibilities for that. So you will never be able to sample everything. And so this is back to your points, Ari. You might not be able to sample the right trajectory to your answer. Okay, and this might affect the performance for this fine-tuning process if you can't get your answer. Okay, so this sampling process is very important. Apparently for the ARC challenge, you just sample the base model many times, you can get the answer already. This may not be the case for other domains. So how can we get a correct generation? Because we want to make sure we get something correct, or at least very, very, very close to correct, so that we can train our model properly. Okay, so once we get the correct trajectories, if let's say we get the ground truth, we can use the trajectory as the data set to fine tune on. Or if you don't have the ground truth, maybe you can use some scoring function, like some LM verifier or something, to, as long as you pass the verifier, you might be able to put in the fine tuning data set as well. So this is something that there's some bootstrap error sometimes, but you just have to hope that in the long run, whatever you use this verifier to put inside your fine-tuning data set, in the long run, most of them are correct. You just gotta hope with that. Okay, so there's a lot of talk about whether some form of tree search is needed to do generation. Okay, so be it train time or test time, should we use tree search to generate? So what do I mean by this is that instead of generating the whole text at one go, maybe we generate one part of it, then we generate the next part of it, maybe the next subtask in a tree like this. And then based on like which path is more promising based on some heuristic score, we expand the nodes here again. So for some like example of how this might be done, you look at the MCTS-R paper, Monte Carlo tree search refined paper. They basically use some form of critic to give a score for each node. And then the more promising nodes, they'll be expanded. And then they'll have a refine step to refine the output for that node and so on. So should we use some form of tree search like this in order to, generate the stuff at training time or even testing time? And the thing is, I've been thinking about this as well quite deeply because, AlphaGo, AlphaZero uses tree search. Why don't we just use tree search for this as well? And actually, there's a small problem. When you talk about AlphaGo or AlphaZero or chess and Go, your moves are finite. If we do tree search for this, okay, can you imagine this case? Okay, there's this discussion later, but I'm just going to give you my view now. Can you imagine a case whereby your verifier biases against the actual answer? Okay, can you imagine that your verifier biases against you? Never select that node in the long run. So maybe this is the answer. So perhaps let me draw in another color. Perhaps your answer is here. Okay, the correct answer is here. But because of your verifier, you keep choosing here, keep choosing this because of your verifier. So there are many ways to do verifier. For more information, you can look at the tree of thought paper, like they talk about breadth of search, depth of search, and also like layer-wise expansion of the search. You have many ways to to be biased by the verifier. Because if your verifier or your heuristic score doesn't select the right path, and you never know unless you try, um, you may not be able to get the answer. So one thing that I realized, because I did some research on AlphaGo and AlphaZero, to play the game of 4 in a row tic-tac-toe. And I think what I realized is like stuff like AlphaGo or Zero is very bad if you start from scratch and they learn the wrong value function. Okay, what is the value function? The value function is like the heuristic for this node as well. So if let's say earlier on in the trials you win by some luck because your opponent is not good, you might think doing this move is correct. And so for the next 1,000 or 1,000,000 games, you are doomed to do that incorrect move. And I think that's also why, AlphaGo, AlphaZero, maybe if you just train from scratch, some iterations will work, some iterations will not work. I mean, some versions of it will work, some versions will not, because they are using the value function to bias the search a lot. And, if you're a verifier, you're using the same one across different tasks, it might be wrong for that task that is different. So, tree search is great if your verifier is great, but in a very general sense, you don't know whether your verifier is good. So perhaps OpenAI is right because they said they didn't use any tree search. Maybe the focus on using tree search will make it fail for some domains. so so maybe we have to sample the whole thing end to end.
Sorry, clarification. What do you mean by start from scratch here?
Or start from scratch means like random weights. Or
Isn't that what AlphaGo Zero is doing?
yes. So what I suspect is that they probably train a few models of AlphaGo Zero and chose the best one. Because I tried to train from scratch, some didn't work.
I mean, you definitely wouldn't have enough compute for.
Oh no, my environment is very simple. It's
Yeah.
a 7x7 board. Yeah,
Oh,
yeah. So I managed to train it in 3 weeks.
okay. But I mean, you commented that OpenAI mentioned they did not use tree search, but from their description, I feel like even they did not use like explicit tree search like tree of thought. The way the model reasons still resembles some form of implicit tree search, right? Because
Yes,
when they
yes,
reach some stage, they might realize it doesn't work, then they backtrack, then try another one. The whole reasoning trajectory and the form resembles of something like an implicit MCTS that is baked into the model by RL, right? So
yes. I'll talk more about it. I have some comments about how they did it. So there's a slide for that. We can talk more then. Yeah. So for this slide, I think what I want to talk about is that, you train by sampling on the correct trajectories, but you try to sample as diverse as possible so you get more of the correct trajectories to train on. I mean, you can also do what the star model did by saying that, if let's say you get the wrong answer, you try to give the hint, which is the correct answer, and then get the rationale and train it on that. Um, just a word of caution, this might give you the wrong rationale quite often, right? So I think it's best to take this path at the top if possible. So this is the train time consolidation. Test time, okay, of course, test time, you can also use tree search to do it. But test time, what has been what at least they have released it on this website here, which is the O1 model. They basically sample multiple samples and just use the most frequent answer. Or if you have a domain with a learn scoring function, you can just rank the answer based on the scoring function and output the best one. So this is a way of sampling a model multiple times to get better answers. So this is very similar to the Ryan Greenblatt methods because he did not do any form of training. Okay, but of course, you could also use this method here. That's why I said earlier, you can also use this method here to assume that most frequent equals correct and use it to fine tune. You can also do that. Okay, but there will be some bootstrap error. So again, there's many ways to do this. I don't have the answer for this, but you can just think about it like which way works best. Of course, if you have the ground truth, that works the best because you have a very, very explicit way to find out whether the trajectory might be correct or not. Again, even if you use ground truth, your trajectory can still be wrong because if you play with LLMs enough, the rationale can be wrong and the answer can be correct. Yeah, it's just like that. So there's always room for error. And the hope is that in the long run, the trajectories are overall correct. Okay, that's what we hope in the long run. In fact, for reinforcement learning, it's the same. Sometimes your policy might be wrong, but in the long run, based on the correction, based on the reward, you will get better and better trajectories. So here, there's no reward. Here, the reward maybe is in terms of whether it's close to the ground truth. Yep. So by fine-tuning on those that are close to the ground truth, you can get better and better trajectories. And this might lead to better and better performance. So this is something that I've been thinking of the last few days and just want to share with you some of my thoughts for this. This fine-tuning process can actually be a form of curriculum learning. Okay, how so? So suppose initially we can only solve like problem type X, and maybe problem type X is needed to solve problem type Y. And so because we fine-tune on problem type X already, when we do problem type Y, one of our trajectories, maybe like one of the trajectories can already solve X. So then we are left with then we just need to solve from the X to Y part. So essentially, if you think about it, if you think about problem solving, if let's say this is the graph of problem solving, you basically don't need to go through too much. Okay, you don't need to go through all the way from like start, this is the start, this is X, and this is Y. You don't need to go through all the way from start to Y. You already solve until X, right? So essentially, you're solving an easier problem now from X to Y. So again, if you can solve Y, then you can maybe solve something like Z. So this kind of way of like trying to solve certain problems, especially if the problems are of varying difficulty, which is what is there in most benchmarks, you can essentially solve the first batch of problems and use that knowledge via reasoning traces. And when you do it when you fine-tune those reasoning traces, you can actually help to improve the boundary of problems you can solve. So another diagram is like this. Suppose this is your initial solution boundary. We call it solution boundary. And then after you fine tune, maybe you expand it a bit because you have the traces to solve more and more things. So this solution boundary expands, and then we expand again. If we fine tune again, we expand, and then we can maybe get this purple, this pink boundary. So it's quite cool because by changing the base model based on correct trajectories, and I put correct in parentheses because we don't know for sure. By just training your model on this correct trajectories, you might be able to expand the solution space of your model itself. And that's what Terry mentioned just now. Like if you put simple problems and hard problems, maybe you might be able to solve the simple problems, then use it to solve the hard problems and so on. I mean, it reminds me a bit of compositional learning. And I think the paper that you need to look at is like, there's this paper called Voyager where you learn skills based on code. Here, you don't learn skills based on code. You learn skills based on your weights. And what weights? You learn the skills based on reasoning traces, based on weights to output reasoning traces. So in some sense, I mean, this is not really discussed anywhere else, but I just think that learning from reasoning traces, at first I thought it was a bad idea because you might, bootstrap wrongly and so on. But the more I think about it, the more I realize that learning from reasoning traces might be a way of acquiring skills. Because if you know how to reason for a certain problem type, you might be able to use that knowledge to do something else. Yeah, so if you train it on multiple diverse problem data sets, maybe there can be some transfer learning using this approach as well, or fine-tuning from the reasoning traces.
I do have some thoughts on this specifically the curriculum learning process for fine tuning. So in theory, if you had this model basically train on this curriculum set, it learns the prerequisites. Would it be possible to continue this fine tuning process, collect enough synthetic data or whatever data that's generated, and then train on that data to create a kind of meta learning? So basically, the model eventually will have enough data from enough curriculum learning to abstract from it and maybe learn how to learn so that it doesn't need to so much rely on hard data, and it can start to abstract more implicit reasoning, such as like how to problem solve things on its own without needing to be, taught, oh, X to Y, then it can do X, Y to Z. It can kind of have that implicit high level reasoning learned from enough of this curriculum fine tuning.
Yeah, that's possible. That's possible. So as long as your data set has a certain structure for your, or rather, as long as you prompt for a certain structure for your reasoning steps, it might be very transferable across tasks, and you might even learn the meta structure for how to get the thinking steps. And I think that's very relevant to the next slide. So before I move on, Derek, you anything else you want to talk about before I go on?
No, that was my main thought about the fine tuning process because I really like curriculum learning. It's a very cool training process.
Right. So I agree with what you said, and now we go on to the crux of how reasoning tokens should be structured. So this is ChatGPT o1. Okay, of course, this is not the pro version, but this is enough to illustrate this point. So instead of, doing a chain of thought whereby your thought is everything, what if you split your thoughts via subtasks? So like, for example, if I give a question like John needs to be at school at 12 p.m. It's currently 10 a.m. He could take the train, which takes 1 hour, or walk, which takes 3 hours. What should he do? So first, the thought process is to map out options. Of course, this is not the real thought tokens, all right? This is just the summary, okay? Because OpenAI doesn't want people to use this for training. So next, we have evaluating possibilities. It's like, okay, so basically they have options. So basically, walking arrives at 3 hours. Okay, taking the train arrives at 11, which is good. Okay, so you can see that this tool here, okay, looks like actually it's doing something similar. Okay, because both talk about different things. And what this does is that, if you want to solve a task, okay, maybe, the detailed subtask should be more something like this. First is list out options. Then you can say that, train is 1 hour, walk is 3 hours, and then, like you only have 2 hours to travel. And then next is reason out possibilities. So Yeah, can only take train because 1 hour is within the time given. So I think this is quite similar to what you see on the right here. I realize sometimes over here the description is not that great, but map out options and evaluating possibilities sound like a great chain of thought for what you have here. So of course, what I suspect for this O1, O3 is that they hide quite a lot of stuff from us. So they might be generating multiple samples. So they might generate like 2 samples and combine the details. So that might be what's happening here also. So we don't know for sure. But I want to go away from like what they do or what they don't do, but I go through this chain of thought via subtasks because I think this idea is quite interesting. So if you train your model to output by subtasks, so for example, I did have a prompt just now that I tried on GPT-4o. You get the different subtasks out by just saying, list out options. First, give the subtask header and then give the description, give the subtask header and give the description. So if you are able to do something like this, you might be able to condition the model to output in a certain format whereby you have a thoughts over here. A thoughts have a thought header for each subtask and a reason and a description for each subtask. And then after that, you can have at the bottom, you can have final answer, which will then give, like John should take the trade. So if we can do an output structured format output by saying thoughts, and in this thoughts, you have all the list of subtasks with the subtask header and the description, and then you have the final answer here. This helps to make the model better able to do a few things. Okay, one thing is that it's able to do some form of planning because model is able to plan the next subtask because you train it to do it this way. Model is able to generate output needed each subtask. And model is able to get final answer based on subtasks. Essentially, it mimics a kind of agentic workflow whereby you do certain tasks, you get the output and so on. And this can be transferable across different tasks. So if let's say you have some PhD student to give the initial like the subtask name and the subtask description, and some of the subtasks could also be, like reflection. Some of them could be, question assumptions. If you can do something like this, you essentially make the model able to do some action and then think about whether the action is correct. If you need to, you can backtrack. If you need to, you can reflect. And all this is done without any research because you are just using text. Okay, you are able to backtrack, reflect, question assumptions, maybe state that, oh, I computed wrongly at first. You might be able to do verifying steps also. Might be able to do verifiers using this method. Okay. Of course, it's not 100% accurate, as my next slide will show you why. But this idea of breaking down your thoughts into systemic, very rigid and systemic processes might be very useful because this is what, you can break down your thoughts, and if your thoughts are wrong, you can change them. This is essentially giving the LM like some form of eraser whereby, if you write wrongly, you can erase it and then correct yourself in the next iteration, which is what agentic systems do. So this native chain of thought will basically improve the base model such that even without the agentic system, it can sort of do some self-reflection on its own and get better quality answers out. Okay, initially I was a bit skeptical of this, but I tried very, very hard to get an agentic system with 4.0 to mimic O1's capabilities. I found it impossible. Okay, so I tried for a few days and I concluded that the base model improvement is needed. So by doing native chain of thought like this via subtasks, you learn quite a lot of things, and you might be able to generalize across different tasks as well. This is quite cool. And let me just stop my share for a while to show you a prompt that I did just now that tries to mimic O1. So give me a while. I'll stop my share and I'll load something. Yeah. Okay, so let me share back my screen again. All right, where's my share? Okay, yes. All right, so I'm just going to load this right now to maybe a new ChatGPT window, and let's not use O1 because I want to show you like how 4O can perhaps do like some form of chain of thought generation. So if let's say we have a prompt like this is maybe the question that was used to make GPT-4o get a wrong answer by putting irrelevant stuff in the math question. Yeah. By the way, can y'all see the screen before I go on? Can y'all see what I'm doing to 4o? Okay, good. So I basically asked it to come out with things in the following format. So I gave it a thoughts field, and then I gave it like the subtask name, subtask result, and so on. And then I give like maybe some prompt like, oh, you need to reflect, verify, and so on. And then I have a final answer here. So what it did, okay, initially it has some thoughts over here. Okay, that's great. And yeah, subtask 1, calculate the cost of erasers, calculate the cost of notebooks, calculate cost of paper, total the cost. And indeed over here, you see you get answer 291. This is correct. So if I don't do this method here, if I don't do this, because you see over here, it talks about price last year, price this year, and so on. So when we talk about subtask 4, when we want it this year, it knows how to retrieve the stuff from the earlier context. Let's say if I don't do this, I just do without this thing. You can see that over here, we have a bond of paper, calculate the cost now, compare with last year. Okay, so sometimes it will give you this answer. Okay, in this case, it got it correct. So in some sense, if you could do a prompt, okay, if you could do a prompt that helps it to do it like step by step in a structured way, it might be able to get a better kind of thinking process, and you might be able to use this whole thing here to do your fine tuning. Okay, any questions before I go back to the slides? Okay, let's go back to the slides. Okay, so I really think this method is quite interesting because you are able to, learn from your data and fine tune with your data on this kind of chain of thought. And, you might even use expert people to come in and write the chain of thought for your pre-training data. So your model is better able to output the chain of thought you want. And yeah, I think this is quite a cool thing that they try to mimic or try to structure the chain of thought by letting the model plan by itself. And all this planning is all done, planning for subtasks and like solving of subtasks, all done by just next token prediction. Can you see this a bit of meta learning here? Like initially we were just trying to predict the next token from web data. Now we are trying to predict reasoning traces from web data, and or rather we are trying to predict our own reasoning traces from earlier. And it is basically something that, I was quite skeptical about this, but after seeing the performance on the ARC-AGI benchmark, I start to think that maybe this method has some merits. All right. Questions or clarifications before next slide? Okay, so what are the limits for this? All right, so of course, we don't want to just use the LLM to do the whole chain of agentic processes to solve tasks and so on. For one, if you ask the LM to, do math, using LMs to do math may not be the best approach, okay? Because it's not very robust with like multiplication, addition, and so on. So you might want to use a calculator. So stuff like this means that we might need to offload certain parts of this reasoning steps to something else. So like a tool, external tool. And external tool use also is not defined here. So if we want to do something like call an API and so on, you cannot just use the LM only to do it. You must interface it with something. So these are two big things that needs to be improved before we can do some more things with this LM. And like asking it to reflect and refine its answer by itself may not be very robust if you do not have a solid verifier to tell it whether the answer is correct or not. So you can look at the LM modular paper for this. This paper basically says that, LMs are not very good critics of themselves. All right, they make mistakes. So using LMs to do its own reasoning has some flaws. And I think it's best if we can still use an agentic approach over this LM so that we can do all these things properly. Like we can call the right tools as needed for all these three things. And that is something that I think um, O1 will likely be the base layer for such an agentic approach. But O1 is quite slow, or O3 is quite slow. So I hope they will be able to find a way to make the reasoning much faster, maybe the model improvements and so on. Yeah, so that it will be more conducive to do an agentic approach that uses a faster processing model.
Actually, I do have an idea about that because I was thinking about it as you were talking, especially your question to ponder. The best approach probably for that would probably to take the agentic approach, but have multiple models that are like your idea from earlier are pre-trained already on the output responses from the other models. But instead of having one model try to abstract all these types of like very complex reasoning, like one layer, you figure out like reasoning traces, and then another abstraction space above it would be like meta learning, trying to build and build on top of top. It's very data intensive, very expensive. So the best approach might be to take multiple models and have them be semi-intelligent. So they learn certain types of reasoning traces on different data sets. I don't know how exactly it would look like or what's the most useful abstraction spaces for them to learn or what types of abstractions to learn from the reasoning traces. But I definitely think the best approach might be a balance of multiple models and then having those models learn a certain level of abstraction from the reasoning. Because if you go too far, then you have a very expensive model, and then every time you want to try to retrain it or slightly tune it a little, it's going to be very complex and expensive, as opposed to having a more simpler model. You can't go too simple, obviously, because if you have a very cheap model, you're not going to have a lot of work with. It's not going to be able to abstract that reasoning that you really need out of it for the make the agentic approach work fully. But those are my thoughts. I think the best approach is a very balanced multi-level models, just multiple models, but have them learn a certain level of abstraction and reasoning for different, it could be different domains, different sects, or different reasoning types, because there are reasoning types. The way you reason on mathematics may not be the same way you reason on social sciences. Social might be more about quick pattern matching, mathematics might be more about implicit knowledge graphing and pathfinding. So those are my thoughts.
Yeah, interesting. I mean, you can use different base models for different agents and see what works best. So I think this LM for O1 or O3 is great to improve the base capabilities for the models, as long as they don't take too long to output the reasoning tokens. Uh, and I believe all this should be able to integrate quite well in an agentic approach as well. Yeah. But I think this part here for chain of thought modeling based on subtasks, I think quite cool because essentially this is something that allows adaptability and reuse across tasks. And since we are on this slide here, I just had a bit of thought here because when we talk about tree search methods, right? So I'm going to spend a bit of time here. I think I won't be able to cover all the slides today. We'll probably have a part 2 next week. So over here, let's say we have a chain of thought here. This is the tree. And what happens is that, based on this tree of thoughts, or like basically this is like your chain of thought in a tree format. So maybe this is thought 1 or subtask 1 and subtask 2 maybe. This subtask 3. If you train on the correct trajectories, right? You are also implicitly training the model to know which tree works. Okay, let me explain a bit on this. So if let's say we train on the entire chain of thought. Let's say this is what we train on, this subtask 1, subtask 2, subtask 3. We train on this. Essentially, based on what you get for the correct thoughts, your tree gets sort of formed. So maybe there's another task that maybe uses like something like this. I may use a different color, something like this. We might use another task that might learn this to solve it. So you sort of, whenever you do Monte Carlo tree search, you have an explore, you have exploit. So essentially, when you do explore exploit, you will base on some indicator like, oh, how many times have I explored this node? Okay, maybe I should go somewhere else. Okay, versus how much value do I get from this node based on the heuristic. So as what I said earlier, we may not have the heuristic that great for all these intermediate steps because it's hard to get a heuristic for arbitrary problems. But if let's say you train on this trajectory like this, your token probabilities will be updated based on how frequent that tree appears. That kind of. So essentially, it is something that I have no proof for, but this is just some thoughts of my head. I'm just throwing it out. Essentially, how much to explore for this side here. Let me use a different color. How much to explore for maybe this tree at the top? How much to explore for here versus here? I'm going to call it branch A and branch B. How much to explore for branch A and branch B can be determined by token probabilities. And this is affected by fine-tuning. Okay, can you see that? So the more you, like, let's say you want to reason with this line of thought, like this tree over here, and you keep getting this reasoning because it's always correct. Because by some filtering of the trajectories, you only filter this as the correct one. Essentially, your model is going to be biased to output this trajectory more and more. And in so doing, you are sort of doing some prioritized search because when you do high temperature sampling, you are still going to sample via softmax over your token probabilities. I mean, you're still going to sample the highest probability more. It's just that you sample the rest sometimes. So you might be implicitly doing some form of exploit by just fine-tuning only on the branches that are good, increasing the token probabilities of like maybe that subtask being generated. And then by keep doing this fine-tuning, you bias your tree search. So this is a food for thought. Could there already be tree search by just fine-tuning on a list of subtasks? Right? I think this is a very important question to ask ourselves, and perhaps people might do research papers on this because there are some disadvantages of Monte Carlo research in the sense that you need to do it in discrete number of actions. If not, it's very hard to do continuous space. All right. So LM's infinite space, very hard to do a prioritized research, but perhaps fine-tuning is its own research. Okay, of course, this is it might turn out to be a bunch of nonsense that I'm talking because, this is something that's unverified. But I'm just thinking about it, like, how did they achieve, like, how did OpenAI achieve those major benchmarks by just simply doing some form of fine-tuning? I mean, I I really don't know how this could be done, but if you think about it, it might be if you bias your training set or bias your fine-tuning data, you might already bias the way the model outputs. And by mass sampling and doing this bias method, it might lead to self-improvement. Yeah, so I think I'll more or less leave it as that because it's quite late already. So next time we will talk more about the results. I think results, like, it's good. It's of ARC. It's doing very well for ARC. It's going all the way until here. Yeah, so 85% is like the human benchmark. So this is pretty cool. it appears that it can transfer to the semi-private data set because like the public data set, 91%, it didn't really lose much of the accuracy. So that's pretty impressive given that ARC problems are all quite different, right? And I think this highlights that there might be something good about the way that they are solving it. So I'll talk more about like the path aheads and so on next time, but I just want to end on this slide. And end on this slide here, where, could it be that having a systemic approach to generate data and fine-tuning on those data, can this be something that is useful to let the model learn and in fact self-improve with certain data? And also, I just want to end on another note. Can we not just do fine-tuning? Can we learn by external memory? So I think that will be the focus for next week when we talk more about systems that can learn by putting stuff in external memory and maybe doing some in-context generation based on the memory. And these systems might learn faster because you don't have to fine-tune. Fine-tuning takes a while. If you use external memory, you will learn instantly. So can we do something like that? And yeah, just going to end here. Maybe last 1 or 2 minutes, any questions, any thoughts before we end the session today?
No, I think I'm all good.
All right. If not, then thanks so much. We'll continue this again next week. And yep, see us.